Hello, and welcome to the IGS University online lecture series. This lecture will be on geosynthetic functions. My name is Erol Guler. Here you have my brief CV. If you are interested, you can read it later on. Before starting the lecture, I would like to ask a question that may also come to your mind. Is soil a construction material? Because we say that geosynthetics are used in contact with soil. Yes, indeed they are, and they are being used in huge quantities. US Geological Survey indicates that in the USA alone in 2019, approximately 1,600,000,000 tons of crushed stone was produced, and out of that, 1,152,000,000 tons was construction aggregate, mostly used for road construction, and this quantity doesn't include the earth materials used in specialty applications like dam construction, marine applications, clay impermeability layers, etc. There are standards organizations who produce standards related to geosynthetics. Here I would like to mention the main standardization bodies. First of them is International Standards Organization, ISO, uh, and its technical committee 221 produces standards related to geosynthetics. Another one is American Society for Testing Materials, ASTM, of which Committee D35 works on geosynthetic subjects, and the European Standards Organization, CEN, and its technical committee 189, uh, which produces standards related to geosynthetics. Geosynthetics are a big family of materials. Geosnatic types are presented in detail in another IGS University online lecture. Here, I would like only to mention the names of the most frequently used geosynthetic products. They can be listed as geotextiles, geogrids, geocells, geonets, geospacers, geomats, geocomposite sheet drains, prefabricated vertical drains, geopipes, erosion control products, geofoams, vertical barrier systems, and last but not least, two very important geosynthetic products, namely geomembranes and geosynthetic clay liners. Geosynthetic functions can be listed as reinforcement, stress relief, barrier, separation, filtration, drainage, erosion control, protection, and stabilization. I have also put a pictogram next to each function, and I will go into a little bit more detail of each function during the rest of this presentation. The first function that I will describe is the reinforcement function. From here on, for every function, I will first give a definition and a pictogram. The definition of reinforcement function is use of the stress-strain behavior of a geosynthetic material to improve the mechanical properties of soil or other construction materials. Typical geosynthetics used as reinforcement are woven geotextiles. Here you see some woven geotextiles and geogrids. Here in this picture you see some geogrids. There are various reinforcement applications, and I will list the ones that are more frequently encountered. These can be listed as follows: to construct vertical or near vertical retaining walls, to construct reinforced soil slopes, as reinforcement at the base of embankments, encasement of soil improvement columns, to reduce rutting in unpaved roads, to provide stability to slope covers, to increase bearing capacity under footings. When we talk about retaining walls or retaining structures, we have traditional gravity type retaining structures, like seen here on this example. Or if you have to create an elevation difference, you can construct an unreinforced slope. And by using the geosynthetic reinforcement, you can have a variety of options. Here you see a reinforced soil wall. This can have a perfectly vertical facing or a facing with a smaller inclination, or even with a larger inclination, in which case we call them reinforced soil slopes. Reinforced soil structure types can be listed as segmental retaining walls, panel facings, wrap facings, reinforced soil slopes, bridge abutments. The first type of reinforced soil retaining structure that I want to mention is the segmental retaining wall. This type of wall consists of two main elements. One, obviously, the geosynthetic reinforcement and the earth fill in between, and the facing elements. More commonly, dry cast concrete blocks are used as facing elements, as you can see also in this picture, and you see the geosynthetic reinforcement and the earth fill. In this slide, I want to show you a few examples of segmental retaining walls. Here is a wall that is 16 meters high and 2,000 meters long. The height is definitely not an extreme height for this technique. There has been much higher walls which have been constructed than this one, but the reason why such a long wall has been constructed using the segmental wall technology is because the cost efficiency of the system, and because its construction is also very practical and quick. As a matter of fact, wherever you have to construct an earth fill anyway, this technique proves to be ideal. In this example of an approach embankment, you see the bridge pier and the approach embankment. So you have to construct an earth fill for this embankment anyway. So instead of establishing a slope, which will use a lot of earth fill material and also will take up the space, for example, which was necessary in this case for this road, you build a wall on the facing of this approach embankment fill. In this slide, you see a residential project where the architect has chosen this technique because it has a very aesthetic appearance. Of course, there are other methods where a full face panel facing is used. Here you see the geosynthetic reinforcement connected to the prefabricated full face panels. Or you can have partial facing panels, and in this example, as reinforcement, geosynthetic strips have been chosen. In some cases, we don't use any rigid facing elements, like we see in this picture. What we do is to use the geosynthetic itself as a facing element. We achieve this by wrapping the geosynthetic reinforcement, so the geosynthetic reinforcement also constitutes the facing. The facing can be perfectly vertical or inclined as seen in this picture. And these type of walls are called overwrap walls. Or you can create also an inclined wall with some rigid facing blocks. And in this special example, they used a certain type of block which also allows plants to grow on the facing. Reinforced slope is a very efficient method to create elevation differences. And in this example, you see the excavator and the huge truck, which gives the opportunity to compare the height of this reinforced soil slope. And this picture has won the IGS photo contest in the previous years. Sometimes we use the reinforced slope for other purposes as well. For example, in this landfill application, here are the geomembranes, as you can see, which we will mention later on. However, in order to increase the capacity of these landfill, a berm with geosynthetic reinforced soil slope was constructed. One of the reinforcement applications are the reinforced soil bridge abutments, as you see in this picture. These bridge abutments are constructed using the soil reinforcement technique, and the bridge deck, as you can see on the sketch, sits directly on the reinforced soil structure. There are many types of such systems where the bridge deck sits directly on reinforced soil. The one we show here on the sketch is a typical type, which is called the Geosnatic Reinforced Soil Integrated Bridge System, or abbreviated as GRS-IBS, which is promoted by the Federal Highway Administration of USA. Geosnatic reinforced retaining walls are very popular in many countries, and the reason why they are popular in Japan is because of their high resilience against earthquake loads. I show here one example of the high-speed train line in Japan, Hokkaido Shinkansen, where in only one single project, a total length of 3,500 meters of geosynthetic reinforced soil retaining walls have been constructed, along with abutments, integrated bridges, box culverts, tunnel protections, etc., where the geosynthetic reinforced soil technology has been used. Another application of geosynthetic reinforcement is in the construction of embankments on soft soils. There are many potential solutions to this problem, and obviously, before the geosynthetics were available, there were also solutions available. I have listed these under the classical solutions. These solutions can be replacement of soft soil with suitable fill, displacing the soft soil, pile foundations, stage construction, or viaducts. There are also many alternative solutions where geosynthetics are involved. A few of them can be listed as speeding up consolidation with prefabricated vertical drains, lightweight fill, or in other words, geofoams, geosynthetic encased columns, and geosynthetic reinforcement at base. Geosynthetic reinforcement at base is what I will look into a little bit more detail. I will mention two mechanisms how the reinforcement at the base of an embankment contribute. The first one is the contribution to prevent a rotational failure. If such a failure plane tends to develop, it has to rupture the geosynthetic reinforcement at the base. So, a tensile force develops which creates a moment around the point of rotation, which is in the preventive direction. And if the embankment wants to spread laterally on this very soft soil, it wants to drag the reinforcement with itself, but in order to be able to do that, it has to rupture the reinforcement. So again, a tensile force develops in the reinforcement that works against the earth pressure. There are many other basal reinforcement applications as well. For example, the sinkhole prevention. Here you see a cavity created by a sinkhole. We encounter these sinkholes quite often. They can be as a result of heavy mining activity or in some cases because of karstic terrain. So if you build a road and the cavity develops under the road, a big gap will develop on the road which can create danger to the traffic. So when you put a reinforcement layer here, it minimizes at least temporarily the deflection of the road, so you have a safe road. Or if the project necessitates some pile foundations under the embankment, in order to prevent the puncture of these individual piles into the fill material of the embankment, we again lay out a geosynthetic reinforcement like seen here in this picture. Another application that I want to mention is the so-called geosynthetic encased columns, or GECs. Stone columns are common soil improvement schemes but have some limitations. If the surrounding soil is very weak, it cannot provide enough lateral confinement. So the stone column may fail either in the bulging mode or in the shear failure mode. So a geosynthetic encasement can be placed around the stone column, and when the vertical load wants to spread the stone column to the sides into the very soft clay, a tensile force in this reinforcement develops and helps confine the stone column. The encasement is also functional to keep the integrity of stone columns under earthquake loads. A very frequently used application of geosynthetic reinforcement is the reinforcement in unpaved roads. When a road is constructed on very weak soil, even trucks transporting materials to the site may sink into the ground, like seen in this picture. However, just by laying a simple layer of geosynthetic reinforcement and some earth cover, the same truck can safely move on this extremely soft and saturated soil. The improvement brought by the reinforcement can be explained by the membrane tension support mechanism, and this mechanism is only valid for unpaved roads. The wheel causes a deformation on the surface, which is followed by the geosynthetic. So the vertical components of these tensile forces provides a support to the vertical wheel load. Why did I say this is only valid in unpaved roads? It's because you need a certain amount of displacement at the surface to activate the tensile forces in the reinforcement. And such a deformation on the surface cannot be tolerated, obviously, in paved roads. There are many more applications of geosynthetics as reinforcement, but I will conclude by just mentioning these two applications in the reinforcement function section of this presentation. One of them is the veneer reinforcement. Here in this picture, the geogrid is used to provide tensile strength for the cover of the municipal solid waste landfill. So the cover will be coming on this layer of geosynthetic reinforcement, but it's not stable by itself. So these geogrids with their tensile strength will help this stability. Or reinforced soil foundations. By using reinforced soil foundations, we can improve the bearing capacity and reduce the settlement of shallow foundations on soils. As can be seen on this sketch, you can use a single layer or multiple layers of geosynthetic to improve the bearing capacity of the soil. Another geosynthetic function is the stress relief function of asphalt overlay. It is defined as use of a geosynthetic to retard the development of cracks by absorbing the stresses that arise from the damaged pavement. As you know, when the asphalt of a road gradually deteriorates, they scrap the top level of the asphalt and put a new asphalt overlay. But since the asphalt that remains in place and the base course has already existing cracks in it, These cracks will quickly reflect to the surface and cause the new asphalt overlay to deteriorate much more quicker. So, by placing a geosynthetic reinforcement between the asphalt overlay and the old asphalt, the cracks are prevented from reflecting to the surface, and the new asphalt overlay can serve a much longer duration. In this slide, I want to highlight how the existing cracks reflect to the surface. Here you see a vehicle approaching the existing crack in the old portion of the road, and as you can see, the weight of this wheel applies a shear stress, so also a shear stress is being applied to the new asphalt overlay. As the vehicle passes directly on the existing crack, it applies a moment which tries to open up the crack as well. And as the vehicle moves away, it again creates a shear force, but directly in the opposite direction of this first one. Also, a contraction in cold weather will apply a tensile force to the crack, and therefore this crack will easily reflect to the surface. So a geosynthetic in between the existing crack and the surface layer will absorb all these stresses. The application of the geosynthetic placement is very straightforward. You spray the emulsion with the classical equipment that is used for asphalt overlay, then lay out the geosynthetic product, and the rest is the normal pavement placement. Another application area of the stress relief function can be seen in the widening of existing pavements. When you have an existing road and due to the increased traffic you want to add a lane to it, then what you do is to scrape the old asphalt surface and then construct the base course, etc. of the new section, and then put a new asphalt. Here is the new asphalt, and here is the overlay on the old asphalt. But because the differences in settlement and behavior of these old and new parts, eventually cracks will occur at the joint between the old and new section, and it will extend all the way to the surface. In order to prevent this, you can simply put a narrow band, for example, a 1 meter wide geosynthetic, to prevent this cracking. Barrier function is one of the most important functions of geosynthetics and one of the very frequently used functions. As a matter of fact, some regulations foresee mandatory use of geosynthetic barriers. The definition is given as use of geosynthetic to prevent or limit the migration of fluids. For example, geomembranes or geosynthetic clay liners are used as fluid barriers to impede flow of liquid or gas from one location to another. Typical types of geosynthetic barriers are geomembranes. Here you see several examples of geomembranes. They are basically polymer sheets or geosynthetic clay liners. These products are unique products where the impermeability function is actually provided by the bentonite, which is sandwiched between two geotextiles. There are various barrier applications. I have listed them under two main headings. One is the environmental applications, and the other are the hydraulic applications. Among environmental applications, we can count liquid containment or pond liners, solid material liners, or as we more often call them, landfills, landfill covers and closures, secondary containments, cover for reservoirs, and mining applications. For hydraulic applications, I can easily mention canal liners, dam isolation, and tunnel liners. I will give you a few examples from these applications in our future slides. Although I will not go into the detail, I just want to mention briefly various barrier geotechnical applications as well. They can be listed as control of infiltration of moisture into expansive soils, maintenance of water content of frost-sensitive soils, beneath structures as methane or radon gas barriers, de-icing salt and aviation de-icing fluid runoff containment, waterproofing of walls and bridge abutments, and to prevent upward groundwater movement in cuts. The liquid containment of pond liners are very common applications of barriers. They can be installed as an unprotected liner, or they can have an earth cover or even concrete cover. Here you see an example where the pond contains contaminated water, and this pond has a huge area, roughly 250,000 square meters. It is lined with a geomembrane. You can get a sense of the size by comparing this pond with the buildings you see around it. Here is a much smaller pond, but this time lined with the GCL versus a geomembrane. Here the pond contains only fresh water for irrigation. This is a very nice country house, and it has what they call an artificial natural swimming pool. And again, the swimming pool here is created with a geosynthetic barrier. Geobarriers are frequently used as canal liners. Here you see a typical cross-section where a canal liner has been foreseen, and in this case it's a GCL. These canals can be used for navigation or irrigation. Here you see a geomembrane liner application in a canal, and here you see a finished canal liner. Sometimes the geomembrane or GCL can be covered with concrete or earth fill. In some cases, it becomes necessary to cover the liquid contained in these ponds, and in such cases, the use of a floating cover becomes very useful. The floating covers are very useful for the following cases: prevention of pollutants in the atmosphere to get in contact with the stored clean water, to prevent gases from a contaminated liquid to evaporate into the atmosphere, or just to simply prevent evaporation loss of the liquid. Here you see a pond full of a liquid and the central float section, and here the peripheral rainwater sumps full of rainwater. When it doesn't rain for a long time or the water is pumped out from these peripheral rainwater sumps, this portion sinks into the water with the help of some additional weights attached at these locations. And when the pond gets fully empty, the floating cover sits firmly on the base of the pond without creating any tensile force in the membrane. Here you see an example of such a floating cover, and to see the size of these ponds that are covered with floating covers, you can again use the scale of these buildings to understand the size of these ponds. There are also tensioned membrane covers, mostly for smaller containment facilities like tanks. The mechanism is explained in this sketch. You have a hanging geomembrane, and there are two examples of such applications in these pictures. Solid waste landfills are applications where geomembranes and geocells are used extensively. Here is a typical cross-section of a landfill with the base liner, and I will mention the closures a little bit later on. Here you have a picture of a geomembrane liner installation, and here a facility that already started taking in solid waste, and you can see the geomembrane here exposed. And here is a facility ready to operate, which has 7 individual cells all lined with geomembranes. In the landfill covers and enclosures, sometimes also geomembranes are used, but in these applications, GCLs are probably more common. And you can see here how easily the GCL is installed as a barrier. In this picture, you see the waste and the GCL cover and the earth cover on the GCL itself. And sometimes innovative solutions can be created, like putting solar panels on geomembrane covers, like seen in this picture. Secondary containment is also a quite frequently encountered application of barriers. You may have underground fuel tanks, as seen in these sketches, or a surface tank, and these tanks have a risk of leaking or spilling, and if they do, they create major groundwater pollution. Therefore, nowadays, the regulations foresee that you build a secondary containment. For example, here, the secondary containment is a geomembrane, or here, the secondary containment is a GCL. Here you see a constructed berm that is also covered with geomembrane, so when there is a leak or overspill, the contaminated material is captured in this small pond. And here is a whole large tank farm which has a secondary containment. The use of geobarriers have become very frequent in mining activities in the last decade, also because the mining technique has changed significantly. Nowadays, in order to extract more metal out of the ore, what they do is they put a heap and then they leach a harsh chemical through it, as seen in this sketch. And the solution collected is flowing into a pond from where it is taken to the recovery plant, the metal is taken out, and then the excess fluid runs into another pond. And from there, it goes back to the leaching. And so this cycle is a continuous cycle. And wherever this leached or harsh chemicals are used, they have to be lined with a membrane so that it doesn't pollute the environment. And here, for example, you see an area where these locations are covered with geomembranes. Also, whatever remains after the process is accumulated in a so-called tailing dam. And here you see a huge tailing dam facility which has been covered with a geomembrane liner. Geomembranes are also used more and more in dam construction. Here you see a concrete dam, an old concrete dam, leaking. And when we say leaking, it's not just simple sweatening or so, but these are like water fountains flowing through the cracks that developed in the concrete. And as you can imagine, this is also dangerous in terms of stability. Similar phenomena can also happen in earthfill dams, and such leakage in earthfill dams is even more dangerous. So the simple solution is to cover the upstream surface of this dam with a geomembrane liner. Here you see a concrete dam being covered with a geomembrane liner. And here it's the finished project, and water has been accumulated behind the geomembrane covered dam. Traditionally, in earthfill dams, as you know, they produce a clay core which is extremely difficult to establish and also prone to many mistakes. So instead of the clay core, The impermeability layer can be created with the help of a geomembrane by placing a geomembrane on the upstream surface of the earthfill dam. And this picture shows the membrane before the riprap is placed on it. And the riprap typically is placed to protect the surface of the earthfill dam. Barriers are also used as tunnel liners, and the amount of tunnels and underground space usage is on the increase because of their advantages, especially in urban areas. When you construct the tunnel, you can have water leaking from water lines, sewer lines, or groundwater. In order to keep the inside of the tunnel dry, we generally put a geomembrane in between the natural environment and the structural liner. Here in this picture, you see a geomembrane liner being placed into the lining system of the tunnel. Not so often, but sometimes also Geocells are used as a liner in tunnels. In this picture, you see a liner system that is not intended to prevent water from flowing into the tunnel, but rather to prevent the water from flowing from inside to the outside of the tunnel. Separation function is a relatively simple but very frequently applied function, and this function serves its purpose very well. It is defined as prevention from intermixing of adjacent dissimilar soils and/or fill materials by the use of a geosynthetic material. For example, to prevent base course materials from penetrating into underlying soft subgrade, thus maintaining design thickness and roadway integrity. Separators also prevent fine-grained subgrade soils from being pumped into permeable, granular road bases. The separation function can be explained with these simple sketches. If this is a subgrade and this is a base course, and if we don't put a separation geotextile, what happens is that the coarse particles penetrate into soft subgrade, and the fine particles of the subgrade migrate into the base course. Thereby, a transition zone of intermixed material is created that reduces the thickness of the base course from its design value to a lower value. So obviously the performance of the base course will be not as good. And therefore, placing a simple separation geotextile helps this base course to serve its function for many more years. The geosynthetics used for separation and filtration can be again woven geotextiles, but more frequently, non-woven geotextiles are used for separation and filtration purposes. Another function of geosynthetics is the filtration function, and geosynthetics are very efficiently and very frequently used for this purpose. Filtration function is defined as restraining of uncontrolled passage of soil or other particles subjected to hydrodynamic forces, while allowing the passage of fluids into or across a geosynthetic material. For example, geotextiles, represented in the sketch here, are used to prevent soils, the red particles here, from migrating into the drainage aggregate or pipe. So the geotextile prevents the migration of these particles while maintaining flow through the system, but water can pass the filter geotextile freely. Filter geotextiles are also used below riprap and other armored materials in coastal and stream bank protection systems to prevent soil erosion. I want to explain briefly the principle of geotextile filters because especially experienced engineers are very skeptical on how such a thin layer of geotextile can provide the filter function because they know granular filters have to have a certain thickness. So when we place a geotextile filter here, what it does is keeping the larger particles in place forming the skeleton, and allow a limited amount of fine particles to escape, and as a result, a filter cake is formed with the help of the geotextile. So again, this is a granular filter actually, which we call a filter cake, but the filter cake is formed with the help of the geotextile. And the beauty of it is, since these are flexible structures, it is very likely that they will undergo deformations due to several reasons. And when the filter cake is disturbed, it can rebuild itself again with the help of the geosynthetic filter. And in this slide, we see a typical application of a highway drainage. Here you see the base course, and this is the drainage trench, which is sometimes also called the French drain. The crushed stone in here is wrapped around with a filter geotextile, and if it's needed, you can also place a pipe to easily discharge the drained water. In this picture, you see the laying out of the filter geotextile, and here the crushed stone and pipes are laid in, and then they will just close this section, and the subgrade will easily be drained from the excess water. Another geosynthetic function is the drainage function. It is defined as collecting and transporting of precipitation, groundwater, and or other fluids in the plane of a geosynthetic material. For example, geotextiles are used to dissipate pore water pressures at the base of roadway embankments, behind tunnel liners, or to discharge gas accumulated below liner systems, which cover large areas. For the geotextile to be efficient to transport the liquid within its own plane, the amount of flow must be limited. When the amount of the to be discharged water exceeds the capacity of a single geotextile, we typically use either a geonet, you see several geonets here on this picture, or a geospacer. Different types of geospacers can be seen in this graph. These are structures where water can relatively freely flow in the voids of their structure in their own plane. But then, of course, we have the problem that soil may fill these spaces and clog it. So therefore, when we use either a geonet or a geospacer, it is a common practice that you also provide a filtration geotextile, which prevents the soil particles to intrude into the voids of these geospacers or geonets. Such a combination we call drainage geocomposite. And here the filtration geotextile serves as a filter, and the geospacer or geonet serves as the drainage media. In this picture, you see a drainage geocomposite being rolled out. As you can see, they are very easy to install. And here you see these drainage materials having been placed around the tunnel. A very common geocomposite, drainage geocomposite, is the so-called prefabricated vertical drains. They come typically in a width of 10 centimeters and a thickness of less than 1 centimeter. They are easily installed into the soft soils. And in this example, I have shown a 20-meter thick soft clay upon which an embankment will be constructed. So let us say the consolidation can be completed in 40 years. And when we install these prefabricated vertical drains, the drainage height reduces from 20 meters, considering that we have an impermeable soil strata below the soft clay, to only 1 meter. That means since the time of consolidation is proportional to the square of the drainage height, the time necessary here is 400 units and here only 1 unit. So a consolidation that will be completed in 40 years, for example, can easily be completed in about 30 days. Another function which geosynthetics serve is the erosion control function. And this function is becoming more and more important, especially because of the climate change. because we know that due to climate change, the intensity of rain has increased, and hence the amount of erosion has increased significantly. The definition of erosion control is use of geosynthetic materials to prevent or limit soil or other particle movements at the surface of, for example, a slope. Erosion is typically caused by rainfall impact and water flow shear stress. For example, temporary geosynthetics or permanent geosynthetic mats placed over the otherwise exposed soil surface on slope can prevent erosion. And these mats typically help plants to grow and stabilize the slope against erosion. In this slide, we see a few examples of erosion control materials. This is a permanent erosion control mat. This is a biodegradable erosion control mat. This is also a biodegradable erosion control mat, but typically these have very small tensile strength, so they have added a geogrid reinforcement to the erosion mat. And here you see a final application of erosion control mat on a slope. Another application is erosion or scour control. We use geosynthetics to protect river and channel banks against scouring by flowing waters, or we can use them to protect beaches against marine erosions. Basically, these geosynthetic products consist of two layers of geotextiles, as can be seen here, which are attached to each other with strings of equal length, these strings. So when you pump in concrete, it basically works as a flexible form, and the inside gets filled with a concrete, as seen here. So you produce a liner, and the beauty of it is you can do this even under the water. Just spread the mat and start filling the concrete, and it settles to the base of the canal or beach, and you can easily form the concrete liner. Here is a picture where this concrete liner has been completed. Or you can have a permeable application if you want water to pass through or even plants to grow in between. This is a grid mat, so when you pump the concrete, these tubes here, as you can see, get filled with concrete, and the intermediate areas are left free for water passage and root growth. Another function is the protection function. It is defined as preventing or limiting of local damage to a given element or material by the use of a geosynthetic material. For example, non-woven geotextiles are used to prevent puncture of geomembranes. Here is a geomembrane, and this is a protection geotextile. By reducing the point contact stress from stones in the adjacent soil, waste or drainage aggregate during installation and while in service, or if you have to put a geomembrane on top of a granular layer in order to prevent the submergence of the geomembrane into the voids or puncturing of the gravels into the geomembrane, you can put in between a protection geotextile. In this slide, we see two applications of protection geotextiles. On the left-hand side, we see an example from a municipal solid waste spill, where there is a geomembrane liner and there is a protection geotextile laid above it. And the function of the protection geotextile is to prevent the sharp objects that may be placed on this layer to puncture into the geomembrane. On the right-hand side, we see a rock armor application on a seashore, and there is a need to place a filter geotextile between the rock armor and the retained soil, so the fine particles don't get washed out. But due to the nature of the filter geotextiles, they have a relatively small puncture resistance. Therefore, under rock armors, also a protection geotextile is needed along the filter geotextile. The last function I would like to discuss is the stabilization function. It's defined as improvement of the mechanical behavior of an unbound granular material by including one or more geosynthetic layers such that deformation under applied loads is reduced by minimizing movements of the unbound granular material. Stabilization can be achieved by geogrids. Stabilization is achieved by the interlock between the materials in the base course layer with the geogrid. This is achieved by a good grid-soil interaction through an optimum sizing of the geogrid mesh to suit the maximum coarse particle size of the soil, which causes interlocking mechanism and confinement effect. Here you see some soil particles interlocking with the geogrid, and here you see a picture of a layer of stabilization geogrid laid out. Stabilization can also be achieved by geocells. Geocells are three-dimensional, permeable, polymeric honeycomb or similar cellular structure made of linked strips of geosynthetics. In this picture, you see a close-up of a geocell with the linked strips attached to each other. And here you see a laid out geocell being filled with granular material, where the cell applies a confinement so that the shear strength of the infill is enhanced. Stabilization mechanisms can be explained by the bearing capacity theory, but researchers state that the lateral restraint mechanism, which is described here in the second graph, is the governing mechanism. This can be explained by, as the wheels trying to push the base course down and to the sides, the presence of this geosynthetic prevents this lateral spreading and thereby creates a confinement effect. I would like to give a few examples for stabilization applications. They can constitute safe working platforms for cranes, piling rings, etc., as you can see on this sketch with the stabilization geosynthetic layer, or as you can see in these pictures. Another application area of stabilization are the paved highways. In addition to unpaved roads, stabilization offers significant benefits in paved highway construction via the potential reduction of aggregate and asphalt layers and/or the extension of the design life of the highway and associated maintenance reduction. Another area of stabilization can be achieved in railways. Railways benefit not only from the subgrade stabilization, but also ballast stabilization, which has been proven to significantly reduce maintenance. In these pictures, you see a geocell and the geogrid being used for stabilization purposes. I would like to conclude this presentation with the following statements. As I have walked you through the different functions of geosynthetics, I believe I was able to show that geosynthetics are used in almost every geotechnical application. A certain geosynthetic product can serve many functions. Sometimes one product can serve more than one function at the same time. The engineer, therefore, needs to select the correct geosynthetic product to fulfill the correct function. Therefore, functions of geosynthetics must be well understood. Another important aspect of geosynthetics is that geosynthetics provide sustainable solutions, and this is especially important in our modern era where sustainability is a very crucial concept, and as a matter of fact, there will be another IGS University online lecture specially dedicated to this subject. Last but not least, one of the reasons why I like geosynthetics so much is because geosynthetics enable innovative solutions. And that means, although there are many specifications and regulations that control the design and application of geosynthetics, there is still room for the innovation of the engineer. Thank you for listening to this presentation and keep following IGS.